All right, well, we'll get started here. Hello, thank you everyone for making it. My name is Joe Giordino. I'm a senior development lead on the Windows Azure storage team. Specifically, my team works with the client SDKs. So if you develop against storage, you've probably seen some of the stuff we shipped. So today's agenda, this whole session is all about performance, throughput, scale, just squeezing the most out of Azure storage as you possibly can. So we're going to cover some best practices on the service, some best practices on the client, the various services, blobs, tables, queues, what you can do. And then we'll talk to some of the new debugging features as well as some of the future directions and what's coming in the next few months. Then we'll have some Q&A at the end. So if you're not familiar, this is Windows Azure Storage. Each region up here is actually a pair of data centers, a primary and a secondary. These data centers are located several hundred miles apart, so you can asynchronously replicate your data to a secondary data center in some sort of geo failover scenario where if, your primary was lost due to some natural disaster or whatever, you'd still have your data. Surrounding this are a whole series of CDN endpoints, so if you need to do content delivery, streaming, things like that. Another note about that map is it's always changing. They've recently announced expansions into Asia, Japan, Australia, so you can keep up on the blogs as to where the new data centers are coming up. So here's the key abstractions: blobs, tables, queues, and disks. Blobs are the file system in the cloud. There's two types. There's a block blob, which is for general purpose files, streaming workloads, things like that. Page blob is for random I/O, so backing drives, which is what disks use to provide a durable NTFS volume. So if you spin up an IS VM or provision a disk in a VM, that's what you're using. Tables is the massively scalable NoSQL data store, so schemaless, terabytes and terabytes of data. And then queues provides reliable and guaranteed message delivery. So we'll get into some more details of each of these later on. So all of these services are available via REST, so you can access it from pretty much any device as long as you can make a web request. We also know that everyone loves writing REST by hand, so we've produced a whole bunch of client libraries for different languages, and we've tried to put as much best practice in the box so you can just get it and get up and running right away. So there's a link there. You can follow that and figure out what language you're developing on and get started. All right, so we'll jump right into it. Scale. These are the scalability targets for a storage account. So when you sign up for storage, you get a storage account. You can have many storage accounts to a given subscription. These apply to any accounts created after June 7th, 2012. You can actually check the account creation date in the portal if you're not sure. The capacity is up to 200 terabytes. The transactions up to 20,000 entities, messages, blobs a second. And then the bandwidth targets for geo-redundant and locally redundant storage are listed there. So ingress is 5 and 10 for geo, 10 and 15 for locally redundant storage. One note about geo replication is that it's part of the billing. So when you set up your storage account, you can have geo replication enabled. And it's roughly 27% cheaper to have it just locally redundant. However, let's say that you go and disable geo replication, and then later you decide, oh, I actually want it back. There is some cost to rebootstrap your account to that secondary data center, transactions and the actual egress bandwidth. So something to think about is, do I need geo replication? And then try to stick with that decision and not toggle it on and off rapidly. Again, these are the targets for a single account. If you need to scale beyond this, many customers use multiple accounts. That's very easy to do. Generally, when you're going above these targets, you start to need to reach a wider audience anyway, and so it starts making sense putting different storage accounts in different geographies to be close to the clients. So here are the scalability targets for our partition. This, again, applies to accounts created after June 7th, 2012. So a single queue is good for 2,000 messages per second. A table partition, which is all the entities in a table that share the same partition key, is 2,000 entities per second. And then a single blob, every blob is considered a partition, is 60 megabytes per second. Again, these are the targets. There is a live load balancer on the back end of the service, so in some cases you may achieve above this, but these are the targets it's always trying to load balance out to. So we have a new flat network design. There's a great blog post here if you want to know more about the hardware and the networking of what's going inside the data centers. From the previous generation to the current generation data centers, they've moved to a 10 gigabit fully meshed network. There's a software load balancer, a variety of different changes, and basically what this all is designed around is enabling high bandwidth scenarios, such as IS disks, high performance computing, MapReduce, HD Insight Hadoop, things like that. So if you want to read more, there's a great link there. All right, so here's a key concept of everything we're going to talk about today, which is the automatic range partition load balancing. So you can see just high up, this is what an Azure storage stamp looks like. At the top there, you have the virtual IP or the load balancer. This is the entry point for all requests. Below that are a series of FE or front-end nodes. These guys handle authentication and handle directing your request to the right partition server. Below that is the partitioning layer. That is what handles all the live load balancing. And that sits on top of the durable file system. So this is what handles replicating your data, making sure that the data is intact, doing geo-replication, things like that. So we'll take a quick demo here. So I've got a whole bunch of different partition servers serving my data. I get a request that comes in, request 1, and it routes it to partition server 3. Now I have another request come in, request 2, that also hits partition server 3. Now at this time, the partition master has detected that partition server 3 is above certain limits, and it decides it needs to reduce the load on that server. So what it's going to do is unassign a range of partitions and reassign them to a different partition server. So now, when I have these same requests come in, request 2 now hits partition server 2. And this is key to everything we're talking about. The more different partitions that you're hitting, the more that the backend can scale out more and more servers to serve your data, the higher throughput numbers you can achieve. So we'll talk about different partition strategies later on as well. One thing to note is the load balancing is triggered on the hot range partitions or the partition servers themselves, and that no data is physically moved on disk during these reassignments. It's just which partition server is actually serving that request. So how's it used? Xblocks is using blobs, tables, and queues for applications like Cloud Game Save, Halo 4, music, Connect data collection. SkyDrive is using blobs for pictures and documents. Bing, they're social ingestion engines. So you may have seen that you can have Twitter and Facebook updates in your search results. They're ingesting all the public feeds from Twitter and Facebook using blobs, tables, and queues to process that and get it back into the Bing search results. It's a really cool scenario. It took one dev about 6 weeks to get that up and running. Skype is using blobs, tables, and queues for Skype video messaging. So this is scaling really, really well for some very large customers. All right, so performance. Couple of notes. All the demos will be using the .NET Storage Client 2.1 RC, and this is going to be available probably next week, available on NuGet. You'll be able to download it, play around with it. Everything's deployed in a production cluster. And the compute is co-located with the storage account, which is best practice. You don't get charged for bandwidth that way, and it's just faster going through the internal network of the data center. And the storage account is created after June of 2012. All right, so client performance. If you've developed against storage before, you may have noticed in the beginning or the end of last year, we released a big 2.0 release, which expanded platform support and really focused on performance. So one quick note here, we had an internal customer that was doing very heavy table workloads. They migrated from the 1.x client to the 2.0. And they basically were able to reduce the size of their VM deployments by almost 3x. And VM to VM, they saw the CPU is probably about half of what they're seeing on the old client. So there's a huge performance gain. We've done a lot of work in tuning this. For 2.1, we are moving even further in both performance and fundamentals. We're also going to hit some highly requested features that clients have been asking for. So a few stats here. Code coverage, last I checked, we're at 91% and counting. There's almost 1,000 test cases. These are all publicly available on GitHub. So if you want to, you can go download them, execute them, or even use some of the code yourself. We have a new performance, automated performance suite that we're running so that we can do live A/B testing against production clusters. And then we can kind of evaluate different features to see are they improving performance, what effects it has on GC, things like that. And then stress. We have a massive internal stress framework, so every single API we ship, we are pushing terabytes and terabytes of data through it, and we're validating things like data correctness, and also looking for those edge cases that are very hard to reproduce. So what happens when there's no more threads available? What happens when you run out of memory? What happens when there's socket exhaustion? Scenarios like that. So this has helped us really identify and fix some very hard to find issues at scale. Again, this is the NuGet location where you can go and download that. It'll be available shortly. So what's new in 2.1? We have async tasks. This is something people have been asking for. So if you're using .NET 4 with the async targeting pack or .NET 4.5, you can now use the async await pattern to do asynchrony very, very easily. We have byte array, text, and file upload and download APIs for Blob. This was something that was in the previous 1.x SDKs that wasn't in 2.0. People asked that we bring it back, so it's there. We have an iQueryable provider for the new table service layer. So this is a query provider that we have written and optimized for Azure tables specifically, and also for a NoSQL environment. So generally, an iQueryable implementation likes to be tied to a fixed type. It likes to know that a given table has a single type inside it, and it does great constructing queries against that single type. We wanted to expand that to be able to do queries against heterogeneous entities inside the same table. And then we have very, very high performance continuations and some other performance optimizations there. We'll get into some more details later. Buffer pooling. When you're running applications at scale, especially people that are running services, being able to reuse buffers really frees up a lot of resources. You're not spending a lot of time allocating memory and GCing, especially if you're using large buffers over 85,000 bytes. You're on a large object heap. So being able to use a buffer pool is really helpful. We also have something that's called a multi-buffer memory stream. So during all of our performance runs, we identified a few bottlenecks in the .NET memory stream itself. And we'll cover a few of those in more detail later. But basically, this stream allows us to give consistent performance, even when the data length is unknown. And it plays nicely with the buffer pool. So again, we're reducing the time that your application spends in GC, which gives you more cycles to do more meaningful work, which should reduce the size of the VMs and the deployment you need to have. The .NET MD5 implementation is now default. Again, the Performance Suite found this out. We released a FSMA-compliant native MD5 implementation for the 2.0 library, which is great if you need FSMA compliance, but it is slightly slower. So in 2.1, we've reverted to make .NET MD5 now default, and if you want to, you can opt back into FSMA compliant if you need that. And then compiled expressions for table entities. This is really cool. What it's going to do is basically write code for you at runtime. So when you're serializing types, you don't have to pay for reflection over and over, which is computationally expensive. And so we'll show you a demo here, but basically you get the flexibility of reflection with the runtime performance of written code. Client logging, and then there's much, much more. So performance, what can you do? Follow best practice for each service. We're going to hit blobs, tables, and queues, and what you can do for throughput and latency. And then identify what you're trying to optimize for. Is it latency? Is it throughput? Is it cost? And plan accordingly. Identify the scalability targets and access patterns. So you're up and running. You're getting 2,000 eddies a second today, which is great. What happens next week when you get 4,000 or 6,000? You need to have a partitioning strategy and a way that your data can grow over time so that you can meet that demand. Use timeout and retry policies to control latency and fault tolerance. So there's a built-in retry policy, but we've also added support for two timeouts. One is a server timeout, and there's also a maximum execution time, which basically says, regardless of network traffic, regardless of retries, I want this thing to be done in n seconds or minutes. I heard one presentation, they said, beware of the retry policy. If you get an error, you may back off and try again and back off, and it could take up to 2 minutes to get the error back. So they were just saying, don't use the retry policy. This is very, very helpful to absorb transient faults, especially if you're on a client device. What's better than just simply disabling it is setting a correct timeout. So now you get the latency guarantee, but the fault tolerance as well. And then use the latest NuGet package when possible. We're shipping to NuGet much, much more frequently than we did in the traditional SDK. So there's bug fixes there, updates as soon as they've gone through testing. And those are always tied to the latest service release version. All right, so here's some general client best practices for .NET. If you're doing any small requests, these are queue messages, small tables, small blobs, you may want to disable the nagel algorithm. What this does, it will basically wait to coalesce requests to the server to fully utilize the TCP window. If you're sensitive to latency, this may be something that affects you. Disable expect 100 continue. Avoid the large object heap when possible. Anything over 85,000 bytes will go in the large object heap. This is more expensive. You can read more about that online if you wish. Reuse buffers if possible. We're going to show you a great demo of how to hook up the existing WCF buffer manager to the client very, very simply in a few lines of code. This will dramatically improve performance and reduce time spent in GC. Use async for apps that scale. So a bunch of legacy apps, kind of a traditional model is spin up a thread to process a request, spin up a thread. Even when using the thread pool, that works up until, let's say, hundreds or maybe even 1,000 requests. When you want to serve thousands and thousands of concurrent requests, you want to use async. The .NET GC specifically, if you're running services, there's a few best practices. We still recommend you target .NET 4 because we've discovered a couple incompatibilities on URI escaping. However, .NET 4.5 is an in-place install, which means you can take advantage of the .NET 4.5 GC while running against .NET 4. So there's a great blog post here about the GC performance, the background GC behaviors. Highly recommend you look at that. And then also use server GC when applicable. The server GC is optimized for these types of scale workloads. So you're going to get multiple GC threads, multiple heaps per core. They just released in .NET 4.5 the background GC for server as well. In some of our tests, this simply turning on server GC probably added about 30% transactions per second on one of the table workloads. For latency sensitive scenarios, consider using sustained low latency GC. So this is a mode that you can use that basically what it's going to do, it's going to use more memory overall. If you're on a server box and you have that, that's fine. But what it's going to do is more frequent, smaller duration GCs. So if you're running a service and you have certain latency guarantees or SLAs you're trying to meet, you may not be able to afford a huge GC pause of, say, 5, 10, 20 milliseconds. So by turning on this mode, you can get much more frequent, smaller GCs, and you won't have that huge blip come in every now and then. All right, as we're supporting clients and evaluating different scenarios, we've kind of compiled a list of different .NET performance gotchas I'd like to share here. So the Service Point Manager is where you're going to disable things like Nagel, set different configuration settings. But these need to be done before the first call to any given endpoint. And the reason why is the Service Point Manager caches the endpoints internally. So if you set some configuration after you make a web request, for example, those configuration values won't be honored. So first line your application, or even in the app config, if you want to avoid some sort of racy initialization, set those right at the top. Default connection limit in .NET is default to 2. For scale apps, this does not make sense. We've actually had some clients come and they say, look, I have an XLVM, a brand new storage account, I'm doing 100 requests at the same time and I'm getting terrible latency. What's going on? One of the first questions we say is, what's your default connection limit? And a lot of times they haven't set it. So what that means is, even though they've scheduled 100 concurrent operations, 98 of them are waiting for a connection at every given point. And so as they wait, the latency that they observe is just increases astronomically. So set that to 100 or more, depending on your setting or your scenario. The .NET memory stream performance is bad for services. If you're using this to buffer data or internally in your application, we recommend you don't. There's a few reasons why. You can actually look at the source that we have for our multi-buffer memory stream on GitHub when it releases if you want to use that. Async performance is not optimal. The read and write byte actually have a comment in the code that says avoid this for anything performance critical. It allocates a tiny buffer every single time you call it. But most importantly, the dynamic buffer size behavior is not great. So I think in total there's like 7 constructors for memory stream. Only a handful of those will take either a fixed size or an underlying byte array buffer. When you use that, you're considered in a fixed mode of operating. All the other constructors will give you this dynamic behavior. And what this means is for data where you don't know the length, it starts with a 256 byte buffer. When you write 257 bytes, it allocates 512 and copies the data. when you write 513, it allocates 1024 and copies the data. For any meaningful size buffer, you've actually done this wasted effort multiple times. For example, a 64 megabyte buffer, you've actually allocated it and moved the data 19 times, and 10 of those buffers are on the large object heap, which we already said we want to avoid. Again, the multi-buffer memory stream in 2.1 solves this and plays nice with the buffer manager. Unbounded TPL parallelism. So we've seen clients hit this when they move to .NET 4. They find out TPL has a lot of great things like parallel for each. And so they just start scheduling lots and lots of requests, but they're not controlling parallelism at the application layer at all. It's not bounded. And so what happens is the server sees a sudden influx of 1,000 requests at the same exact time and begins to throttle. What you want to do is just best practice for all of your applications is to give yourself that knob to control total concurrency at the application layer so that you know how many requests can be done or outstanding at every given point. There's a blog post on the bottom there that actually shows you how to write a task scheduler with the code that will actually only allow n concurrent things happening at a time. One other bonus one on that is if you're using cancellation tokens and you're registering the delegate, you may want to make sure to deregister that. Because it'll hold on the objects and you'll start leaking memory over time. General server best practices. You want to locate storage accounts close to users. Obviously, the closest you can be is inside the same data center. So if you're running a compute workload, you want to make sure that the storage account is on the same data center. This way, the networking is incredibly fast. You don't get charged for the bandwidth. Outside the data center, you want to be geographically close to users. So you wouldn't deploy to Dublin if you're supporting people in, say, America. For widespread client apps, you may want to consider using multiple storage accounts in different localities and serving different data out of each. And then if you're trying to hit a more global audience, especially for blobs, consider using the CDN, which will cache that data at all those different endpoints close to users. Understand the account scalability targets. Again, this needs to be part of your planning for scale out so that as you get more and more data, you have a plan to potentially use multiple accounts, what kind of bandwidth peaks you'll see throughout the day so that you fit with these targets. And then enable logging and metrics on each storage service. So there's more information here and also on the Azure storage blog. But basically what this provides is a whole bunch of information for you to self-diagnose and monitor the performance of your application and any requests made to your storage account on your behalf. This is particularly helpful when you're using shared access signature and giving permission to someone else to access storage on your behalf so you don't control the client. This can be done via REST, the client API. Also on the portal, it's incredibly easy. It's just a few buttons to click. Something important to note is that the data can be automatically garbage collected according to a retention policy that you set. So you can basically say, I need logs maintained for 7 days for only put requests, for example. After 7 days, you won't be charged for the transaction. The server will go in and GC those logs for you so that at any given point, you're only paying for the storage of the logs, which, depending on what you log, can be quite small. All right, optimize what you send and receive. So for blobs, rather than downloading the entire blob, you may be able to do a range read for maybe the first handful of bytes, depending on what you're checking. You can use metadata, so I can tag my blob to say this is in a given state of processing, et cetera. So now I can list those blobs and get the metadata without having to download any data. Or head requests, I can get the content MD5, the content length, things like that. For tables, there's upsert. The upsert semantic basically says, I don't care what's on the server. I either need to insert this or replace it or merge it. And by doing that, it saves me the round trip of having to say, does this entity exist? If so, possibly delete it, then stick something else in there. And any possible optimistic concurrency failures that might happen there. Merge, if I have a very complex entity, let's say it has 200 properties, I don't want to download that entire entity, modify just one property, and then upload the entire payload. If I use merge, I can just update that one property, say gamer score or account credits or whatever, without having to round trip that entire complex entity. And then server projection. By doing this, I can pre-filter what the server is going to send back to me. That not only reduces the time to parse, but there's fewer bytes sent. So you get lower CPU, lower latency. And then point queries. By identifying your data down to a single entity, rather than having to iterate potentially many, many rows, the fastest lookup is a point query where you know your partition key and row key. For queues, there's the update message semantic. What this does, so rather than having a message in a queue, deleting it, and then inserting another message in a different queue saying, okay, stage 2 of processing or something like that, I can use update message to just checkpoint my work into that existing queue message over time, which also is nice in the event of a failure so that the other worker doesn't have to start completely over processing this request. But it also, in the end, you use less transactions for that given queue. And then you can tune the batch size to see how many messages you peak or get at a time. Distribute your load over many partitions. So going back to that scale demo, if you target your data access to always be a single partition, you're going to be limited by a single server. So for example, for tables, if I used a constant for the partition key, that means all the data for my entire table will only ever be served by one server, and a single partition's scalability target is 2,000 eddies per second. That's fine if I can live within that target, but you may consider using a better partitioning strategy for growth over time. One note about that, table entity group transaction, or batch, only works for all the entities that have the same partition key. So this is a really great feature if you want to do an atomic update of multiple rows. So I can debit the account credit and insert an order in an atomic operation. But when you're considering your partitioning strategy or key selection, you want to think about that. And then control parallelism of the application layer. We kind of already talked about that briefly. And then blend traffic types. So in general, blob workloads tend to be more I/O bound, and table workloads tend to be more CPU bound. So generally, people are planning out their scenario. They'll say, I have my 5 blob workers and my 10 table workers, and they're doing these different things. By putting those in the same VM or role, now you can make better utilization of the same VM, all the resources available, both CPU and network. All right, so we'll jump right into blobs. Best practice. A blob is a single partition, which is good for 60 megabytes per second. You want to choose the right block size for your scenario, so there's some client different properties there to how to configure what you write and what you read. We'll do some experiments about that a little bit later. And then use seekable streams when possible if you're using the client API. The reason is, for unknown length of data, anything over 64 MB has to be uploaded as a series of blocks followed by a put block list. Anything under or up to 64 MB can be done in a single atomic put. When the client does not understand how long the data may be, it has to use that block behavior. So if, let's say for a very small blob of, say, 10 kilobytes, it's actually going to do a put block and then a put block list, which is 2 transactions, which is, in general, almost twice the latency than just having done a single put blob with 10 kilobytes in it. So especially for small streams, try to use seekable streams. The new byte array APIs make this very easy because you can do a read and just pass in the byte array directly. Use async for scale. Again, this is dramatically simplified with the new task APIs. And the 2.x clients have a much improved download and download resume behavior with fault tolerance built in. So by migrating to a 2.x client, what it's going to do is you'll initiate a download, and if a fault happens, what it's going to do is issue a sub-range to complete that request, tracking how much data it already has. And then at the very end, it's going to validate data integrity using the content-MD5 to see if there's any sort of faults. By doing this, you can get the most efficient, the fewer number of transactions for your account, but also the highest throughput. All right, so what are the improvements in the client for 2.1? The byte array upload and download APIs. Also, there are range APIs for streams, for example. So now, if I have some source stream and I need to hit multiple blobs, I can say just upload a megabyte out of this stream or some chunk out of the byte array. So you don't have to pre-buffer data in that sense. An asynchronous stream open. Again, the .NET MD5 implementation is now default. You can see the flag there if you need the FSMA compliant MD5. Multi-buffer memory stream, and then the iBuffer manager. I kind of hinted at this before. We patterned iBuffer manager after the buffer manager implementation in system.service model. So if you're on a desktop environment, you can hook up buffer pooling in just a few lines of code. For other platforms like phone and Windows RT, you can program against the iBuffer manager interface. It's incredibly simple. All right, so here's some example performance data. Again, this is against 1.7 and the 2.0.5.1, the latest release, and then the 2.1 RC. So upload latency is down by 16.5% for sync, and async about 5%. Download is decreased by 23% and 37% async. And then CPU is dropped by almost 40% across all these scenarios. Something else to notice here is that 2.1 versus 2.0, the latency is only dropped by just a handful of percentage points. We looked at this, and basically we are truly network bound. We've removed the client out of the critical path, and now you just have more and more resources. So achieving the same latency for those operations, you can see that we've still decreased CPU by close to 13%. The test setup here is just an XLVM with 30 concurrent blob workers uploading and downloading 256 megabyte blobs at a time. All right, so throughput. A single XLVM can achieve 1 gigabit approximately to the blob store. A single partition can provide 60 megabytes per second. So what does this tell us? Use multiple blobs. If we want to achieve maximum throughput, we want to target as many blobs as possible, as many partitions as possible, to be served by multiple servers on the back end. So by doing this, you distribute the load over those partitions. Longer lived connections allow the TCP window to grow, so you make more efficient use of your connections to the server. Blobs under 64 MB can be uploaded as a single put. Fewer transactions, fewer cycles to authenticate, things like that. And then this also avoids the long tail problem. So assuming you have an 11 megabyte blob with parallelism set to 10 and 1 megabyte blocks, all things being equal, the first 10 blocks will complete roughly at the same time. And then you'll have to wait for that single 1 megabyte block put and a put block list before you move on. So we're going to look at comparing for throughput. Is it better to use parallelism at the blob layer or upload multiple blobs or access multiple blobs at the same time? So let's do this. We kind of already hinted at the answer here, but what pattern is faster to upload n blobs? I can do 1 concurrent upload with parallelism set to 30, or I can do 30 concurrent uploads with parallelism set to 1. Let's find out. All right, so my test setup is an XLVM. I'm uploading 512 256 megabyte blobs. They're using a 1 megabyte block. This is approximately 128 gigabytes. All right, so just as a benchmark, just doing a single operation, you can see this whole scenario took approximately 10,000 seconds. I averaged 13.23 megabytes per second. So we improved this by enabling parallelism per blob. So we're uploading 1 blob at a time, but potentially 30 blocks at a time. And that averaged about 50.72 megabytes per second. By uploading 30 blobs at a time, just doing 1 block at a time, now I've almost doubled that throughput to 96.64 megabytes per second. The test completed almost twice as fast, and no matter what, a single blob is always going to be bounded by the limit of a single partition, right? So by accessing multiple blobs, we'll be able to scale out. So the next thing people ask me is, okay, that's great for parallel upload. Where's parallel download? And the answer is it's not there. And it's not there on purpose. A couple of reasons why. One, this would require much bigger memory footprint in your client application. So you can imagine us doing multiple parallel download requests. We'd have to keep these buffers in memory to be able to order the bytes correctly to write it to the destination stream. And then secondly, in our experimentation, it didn't actually provide a significant performance improvement. So we'll do a quick experiment around this. So I'm going to flip over to my live VM here. So what I've got here is I've already uploaded a 1 gigabyte blob, and I'm just going to download it using a single get. And I've got Task Manager there. So I'll click on Ethernet here. You can see I'm right about 1.2, 1.3 gigabits per second. This is actually above the 1 gigabit limit per VM. But doing a single get, I'm able to achieve basically the full networking resources of this VM. So doing that parallel download isn't really going to help me much. So in this other example here, I was able to download that gigabyte blob in 7.8 seconds. That averaged 130 megabytes per second. One thing to note about this is over double the scalability target for a single blob, which is fine. That was actually great to see. However, this is a multi-tenant system. And what that means is I can't take a dependency on any performance that I observe above the scalability target. Because tomorrow, later this week, as I become co-located with more data that's more noisy, the load balancer is going to try to achieve those scalability targets. So if I made some sort of dependency on always getting 130 megabytes per second out of this blob, weeks later I might run into an issue there. So again, always code and program against those scalability targets. All right, non-seekable streams. So we had a client that came to us that was doing something very similar to this. They basically had set up a proxying service so that they didn't want anyone to know what was going on in Azure on the back ends. They just had an API, and you could upload files, and they would store them in blobs. The problem is a lot of these files are very small, and they were just handing the network stream to the client, which was non-seekable. So we replicated this scenario, and they were seeing kind of higher than expected latencies. So we're going to upload 10,000 10 kilobyte blobs. And what we did is we took the same stream and we just overrode it to return true or false for the can-seek flag. So the same underlying implementation. And here's what we found. The single put blob is always better for smaller blobs. Non-seekable stream, almost twice as bad. Again, for those smaller blobs, you have to do those 2 round trips, put block and put block list. This is when you do that, you're going to have to pre-buffer the data as well. Again, 2 times faster, so if you have small data, try to use a seekable stream. Block read size. So now people ask, what's the most efficient way to access my blobs? So here's a quick experiment about this. We have a 256 megabyte blob that was uploaded with a 4 megabyte block size. So I'm going to start downloading this in very different ranges. The first one is a single get. In this case, I averaged about 85 megabytes a second. Then I started reading in 4 megabyte ranges, then 2 megabytes, 1, 512, 256, 128, all the way down to 64K. When I started doing 64 kilobyte ranges, I was down to 8.69 megabytes a second, so almost 10 times slower. The reason why is I have to do multiple round trips, authenticate multiple times, potentially reestablish the connection depending on what sort of network I'm on. So in general, the larger read size, if you're going for throughput, the better. One note about when you're choosing a block size to upload, a block blob can contain 50,000 blocks. And what this means is your choice of block size, which you can have different size blocks in the same blob, but the size of those blocks limits the upper bound of how much a block blob can store. So for example, if I use 4 megabytes as my block size, I can store 195.31 gigabytes. If I use 2 megs, I'm down to 97.6. If I use 128K, the maximum blob size is 6.1. So something to consider when you're choosing the block size to upload. All right, so we'll jump into tables. What's new in 2.1? We have the efficient iQueryable. We'll show some code here and how you can do some of the cool shortcuts for projection and the dynamic query construction. Compiled serializers. These are roughly 40 to 50 times faster computationally than reflection at runtime. More flexible serialization, so we have an ignore property attribute. So now if I have a POCO entity, and maybe I'm binding it to a UI, for example, I can ignore and just opt out 1 or 2 of those properties. And then we've also exposed the default serialization logic to the user as a static method so that you can use it against third-party objects that know nothing about storage. Right? So let's say I have a DTO object in a service, and I don't want that to expose any sort of Azure-specific knowledge or functionality. Now what I can do is use this runtime serialization logic, which makes use of all these optimizations with compiled serializers, etc., to serialize that DTO type without having to have another service entity and marshal between the two. So I can actually have a middle tier service and directly take a collection of DTO objects that know nothing about table storage and serialize them into table storage using these methods without writing any sort of serialization logic myself. And then the multi-buffer memory stream and buffer pooling, again, for performance. So let's look at some numbers compared to 1.7 and the last 2.0 release. These are complex single entity operations. So my test setup, I have a whole bunch of workers. I'm uploading, downloading, and deleting 150,000 complex entities, so they have all the different types and I think 30-something properties via single operations. So you can see 1.7, 2.0.5.1, and 2.1 RC. So you can see we've driven down latency significantly, and compared to 1.7, CPU is down almost 40% in this scenario alone. We have similar reductions in entity group transaction or batch So again, you can look at that as well. So table performance best practice. Key selection is the most important thing you're going to do that impacts performance ahead of time. When you decide what you're going to use for partition key, you're essentially determining your partitioning strategy. When you also think about how am I going to need to query this data, those partition keys and row keys are very valuable. You need to think through what do I need to choose there, how am I going to access this data later. You want to send and receive the smallest amount of data necessary, again using merge and upsert when appropriate, and server-side projections when querying data. And then use the table service layer in the new 2.0 clients, 2.1, over the WCF data services because it's got a ton of optimizations specifically for Azure and Azure tables. And there's a bunch of other work that's happening here that'll be getting better over time as well. So query design and selectivity. One thing you need to understand is continuation tokens, specifically when querying data. So as you're querying data, let's say it's hosted by many, many servers, you'll get continuation tokens when certain limits are hit. So when you've got 1,000 entities already in the return payload, when the payload has reached 4 megabytes, when you've hit a server boundary and you need to start iterating on the next server, or at certain timeout conditions as well. So in general, you want to minimize those continuation tokens, which are going to necessitate another request, as much as possible when you're trying to achieve high throughput. Table scans are expensive, so you want to avoid them for anything that's latency sensitive. A table scan basically is a query on an unindexed column or something that has no bound on the partition key. So as my data grows, as it's hosted and served by more and more servers, the latency of that request is going to get slower and slower because I'm going to have to iterate every single entity on every single server. As my data grows, this gets more and more expensive. So we have kind of the in-order performance of queries. Point query, where you have your partition key and row key of the entity, is the fastest. The row key range query, so I have a fixed partition. At max, this is going to iterate through one server. And I've bounded the row key between A and D in this case. Row key range query open-ended. So now I have row key greater than C. So now I've given it some number of entities to skip, but I'm still on a certain partition. And then a multi-partition query. So I have my partition query, my partition key bounded by an upper and lower bound. I may hit multiple servers. I may get multiple continuation tokens. And then a query on a non-indexed column, timestamp, a user column, first name, things like that, is going to be the slowest. All right, so tables. When you're trying to optimize for throughput, batch size is your friend. Batch will perform atomic actions, given that they all have the same partition key. This is really, really nice for various scenarios. On top of that, you can get a higher overall throughput and lower latency per entity by using larger and larger batch sizes. So we'll do an experiment to kind of see what the optimal batch size is in a second. A batch can contain up to 100 entities and can be up to 4 megabytes in size. Insert operations, something to note about these, is that they return the entity back to the client. So if you don't need that, if you can use the upsert semantic like merge or replace, you won't get that payload returned back to you. So that's less bytes to download, less bytes to parse, lower CPU. And then latency, query selectivity. The smaller the take count / page sizes, the fewer number of entities that I have to iterate potentially in the server, the lower latency. Projection, again, take only what you need, especially when you're receiving a large number of entities. Reducing the size of that payload is helpful. And then avoid expensive serialization and deserialization. We have a couple different options in the 2.0 libraries. There's a dynamic table entity to avoid creating these huge objects with lots of properties. So it's basically a hash map approach. And then 2.1, again, with the compiled serializers, can dramatically improve performance. All right, so let's answer the question, what is my optimal batch size? So we've done an experiment here, and you can see here that the latency for the entire request and the latency per entity, what happens. So you can see I kind of peak out right about 20 to 25 entities per batch. Again, this depends on how big my entity. I start to achieve highest throughput. And so what I can do here is we can see this running live in production. So what I've got as a tool And it's going to start doing a whole bunch of uploads at various batch sizes. So I can zoom in here. So you can see here, when I'm doing a single batch size, I'm getting about 14 milliseconds per entity. When I'm doing 100, I'm down to about 1.4. You can see it right about, my VM's a little slow here. Right about 20, I start to get down to that 2 millisecond range. All right, insert versus insert or replace. Again, we talked about insert or replace or the upsert semantic, not having to download that entity and transfer that data and parse it. Actually, I skipped that. So if I log back into that VM, I've got the exact same worker set to insert entities or insert or replace. So I'm going to start 20 workers uploading the exact same data. You can see at the top here I'm averaging per entity latency of, let's say, 3 to 4 milliseconds. Down here I'm closer to 3. So this guy is achieving, let's call it 4,500 entities a second. This guy is a little over 5,000. In some of our tests we've seen 6 and 7 there. So again, when it makes sense, use that upsert semantic. There'll be future optimizations coming in this as well in the future. All right, so now it's time for some code and the cool features, specifically around tables. So I'm going to switch over to Visual Studio here. All right, so what I've got here is a tables application, and we're going to try to show a few different things here. First thing I have is that customer DTO object, which knows nothing about table storage. This is something I could serialize. It could potentially be an object from some third-party library that I don't own the source to. But I still want to persist it to the table store. The second thing I have is an order entity. So this does know about the table store. It's maybe some sort of internal type. But I want to work with these both at the same time with storage. So a couple things. Let's start this up. The first example here, you can see that I have a whole bunch of these customer DTO objects I'm going to define. But then I want to figure out how to serialize these. So what I've done is I've created this entity adapter object. And all this object does is redirect the serialization logic to those static methods, right? So I have a simple object. I have an entity adapter of type T. I have this constrained to where T is newable or iTable entity. But I don't have to have this iTable entity if I don't want. So as I construct this object, I simply store that inner object. And then I have, in this version of the code, I basically have a mapper function that will map the partition key and row key to that DTO object, because they don't define those properties. So now during serialization, deserialization, I can read and write those properties appropriately. So if I execute this, well, you'll see here, I'm actually registering this type so I don't have to pass in these functions multiple times. But basically what I'm saying is I'm going to use customer ID as my partition key. When I'm reading it back, I'm going to set that partition key. And then for my row key, I'm going to use last name, semicolon, first name. And then again, when I read it back, I'll split that out and populate that entity again. So from here, I have this customers. Again, envision me as a third middle tier service here. I can actually take the data right over the wire, do a select, and grab these table operations right out of there, and then execute them against table storage. So I'll do that. Now I'm actually going to query this, and because customer DTO doesn't have all of the properties, for example, partition key or row key, I'm actually going to create this using dynamic table entity. And there's some really cool optimizations here, but basically what this lets you do is construct a type-safe query without having to define all of those types for the different properties. We'll show a couple more examples about this. All right, so my mouse is wigging out here. So what I've basically done is use the entity resolver, which is the client-side projection. As I read those pieces of data out, what I can do then get back to the code here, is I can choose what type of entity I want to use to deserialize, so I can peek at the data. So right here, this is a customer entity. I'm just going to print that out. You can see that on my little application. I was able to persist these entities to the storage. All right, so now simplified projection. We'll look at how we're going to limit what data is returned by the server. So traditionally, in a link query expression, what you would have done for projection is you would have done a select new, and then you would have say entity A equals A, B equals B, C equals C, all the way down. And then it would be smart enough to say, okay, he accessed the A, B, and C properties. That's what he wants to filter on the server. What we've done is we've separated the ideas of client-side and server-side projection and offered those up in kind of separate places. You can still do select new if you want, but we have a couple optimizations here. So the first thing we have here is this table query.project. So by simply giving a params of all the properties, I can execute this query, and it will only bring back the first name and last name, as well as the row key, partition key, timestamp D tag, which are those reserved fields. So you can see when I get that same data back, I have those names, but not the email account balance and rating. So now I'm going to populate a whole bunch of data in my NoSQL table. So for every customer, I entered a whole bunch of orders. And now what I want to do is construct a query on both customer and order types. So if I was doing this in traditional link, or I would have to have some sort of Uber entity type that was customer order that had kind of the union of the property types for both of those entity types to be able to construct the query and know the types for each property. By allowing to create a query against a dynamic table entity type, I don't have to construct that big entity. So if you look at the syntax here, what I've done is I've accessed the properties property, which is basically a dictionary of the properties on this entity, and I'm going to pass in a param of first name, and I'm going to access it as a string value. And then I'm going to do my filter clause. And now I'm also going to access the account balance property as a double. So what the iQueryable is smart enough to do is actually pull out that param and check which method you're accessing it as a string, as a double, and create that type Swift query for you. So now without having to create this huge entity object, I can query across multiple entity types at the same time. So you also notice I have this resolve extension here. So this is what we consider client-side projection, which essentially is mutating the data on the client side. So what I want to do here is I'm querying for both customer DTO, but also order objects. And I'd rather than getting some sort of dictionary or some sort of Uber type back, I would like to have a heterogeneous query. I'd like to have those customers and those orders. So what this is going to do is peek at the data right off the wire before it decides what type to deserialize into. So you can see here, what I'm going to do is say, if this has an amount, it's an order. If it has a first name, then it's a customer. This is going to set those properties and call read. Now what I can do is when I execute this query, I'm going to get customers and orders and write them out appropriately. So you'll see here I have orders. If I scroll up there, I get the customer as well. Okay, so one cool thing to look at. If we look at my table entity type here, there's a couple interesting things. There's a compiled write cache and compiled read cache. And if you look at this, for the two types that we've serialized here, it's actually compiled a func that actually knows how to take an entity and serialize it, as well as an action that knows how to read back that entity. So it's as if you had written the code to go say, A is property A string value, for example, for every single property in your entity at runtime. So you paid reflection once for the entire lifecycle of your application, and then from then on, it's actually compiled code. You can disable this if you want, but there's dramatic performance improvements here. All right. All right, so for more table resources, there's the table deep dive there. This will get into key selection and how you're going to access your data, all the internals there. As well as the table, how to get the most out of table storage blog. Again, I recommend you read both of those. All right, so we'll jump into queues. Again, Niggle is important here, as messages may be small. A lot of messages will be just a URI to a blob, so this may impact the latency. Design your application to update messages when it's appropriate. For scale, use multiple queues, and we've actually got some sample code that we'll release here that is a multi-round robin queue, so you can target more than one queue greater than 2,000 transactions a second. And then use the message DQ count to detect malformed or poisoned messages. So, for example, I have a whole bunch of workers that are using queues for their guaranteed message delivery. As I get this poisoned message, when I begin to process it, for whatever reason, it causes my role to crash. I have a bug in my application. Now, what will happen, because it's guaranteed message delivery, I haven't deleted that message, it'll become visible again in some period of time. Now another role is going to pick up this message, and it's going to try to process it, and it's going to crash too. If I have enough of these poisoned messages, I can essentially DOS my entire service, as all my roles are constantly crashing. So instead, when you get a message off the queue, you'll get two things. You'll actually get the pop receipt, which is how you go back and delete it, but you'll also get a DQ count. So now you can basically ask the server, how many times has this message attempted to be processed? And you can set some sort of limit, like try 3 times. And then maybe what I'm going to do is take this message and stick it over here for some user or somebody to investigate later. And then I can keep my roles processing all the correctly formed messages. So for throughput, tune message count for peek and get. You can get up to 32 messages at a time. You can get higher throughput by getting more messages at a time, but consider the failure mode, because if I fail on that first message, those 31 other messages are also invisible for some period of time, so workers can't be processing them until they become visible again in the queue. You can tune the initial invisibility time and the visibility timeout. This is how long that message is invisible in the queue. The lower the timeout, the more responsive your roles have to be to go back and make sure they delete or update that message. Otherwise, it may become visible again while it's still being processed, and you may duplicate effort. And then use multiple queues. So multi-queue strategies. Something we see a lot is that clients will say, I have 10 workers, therefore I have 10 queues, and I'll put work in these queues, and each worker will take messages out of that queue. This is fine. It's very simple. There's a couple edge cases where this can kind of fall down, specifically in the scale up and scale down scenario. So now I potentially have to drain a queue if I need to scale down so I don't lose work. And then my workers have to know specifically what queue that they're assigned, things like that. So something else we recommend, and we have some sample code here, is a round robin queue. So what this is going to do is have a collection of queues that all share the same prefix so they can be created and deleted together. And then it's going to spread out all of the work across all the queues. And so now my worker is not bound to a single queue. So for example, if I had worker 1 that's tied to queue 1 and it has no messages, while queue 2 has thousands of them, that worker is sitting idle. By using this round robin approach, it's going to keep going until it selects the next queue that has data, and that way I don't waste those VM cycles. One note about this, latency can be higher in some cases when you have empty or near empty queues, because it may check multiple queues to find a message. We already talked about the invisibility timeout for latency, smaller message count for peek and get, and then using multiple queues. So same thing as tables. What's the optimal number of messages to get? So you can look at the latencies and latencies per entity graph here. You can see as I get to kind of 8 or 12, I kind of level out where I start achieving that kind of peak throughput. All right, so let's jump into some of the debugging demos. In the 2.0 clients, we have an object called operation context. This is your friend. Anything that you need to know about what's happening to the storage service, this can tell you. So it's available for the overload, in the overload of every single message that'll make a request or multiple requests on your behalf to the server. You can add custom headers. You can add a client request ID, which will show we can correlate with server logs later. And then it actually will store information about every request that it made on your behalf. So you can go back and look and say, how many times did I retry this? Did I get any exceptions? What was the performance of this specific request? You can make better decisions during retries by looking in history to see what sort of performance you're seeing. And there's also events for send and receive, so you have access to the HTTP web request and the HTTP web response. So if you need to look at headers, you can do that as well. In 2.1, we're introducing logging. So we have kind of an interesting model here. A lot of times in traditional .NET applications, what you do for logging or tracing is you'd say, enable it for this class. And that's fine. You can still do that. However, for scale apps, and especially if you're persisting these logs to storage, turning on logging, and especially very verbose logging, can sometimes make your scenario go away that you're trying to find because you now have so much throughput and cycles spent on the logging itself. So we wanted to enable targeted or vertical logging for specific web requests. So what we've done, you configure your listener here, and you set the max verbosity that it's going to log. But then what you can also do in your application is set there's a static operation context at default log level. You can actually set that to any verbosity. So now if I want to have an opt-in model, what I'll do is I'll turn that to off. And then for my specific requests, let's say my small blobs are taking longer than I expect, or my large blobs, I can now pass in an operation context that said, log this guy verbose or just informational. And now only that request gets logged. And so now I can target my logs towards only the requests that I find interesting. So let's look at a demo here. All right, so I'm going to purposely do an operation that I expect should fail. So you can see I've done this opt-in model, so I've set the default log level to off. But I care about this one operation because I know it's kind of buggy and I want to log it. So I've created a context, I've set it to verbose. So now what I'm going to do is I'm going to upload an 8 megabyte blob with very small block size, so 16 kilobytes in this case. And I'm also going to send in a ridiculous timeout of 2 seconds for all these many, many small requests to happen. So I'm expecting that this won't succeed. So I start executing here. Oh, I get an exception. That's expected. So a couple things to note here. I can zoom in here. The exception itself actually is going to store the request information. So you can see here I have information as to the exception, potentially the status code and message. So that's helpful. But then, if I look back over at my operation context here, what you'll see is that it actually has a request result for every single attempt. So I have 16 of these, right? So I can look back through time and say, okay, this one was successful, it's created, it's 201. I also get the server request ID. So this is what I can use to correlate this specific request with the server logs and see what did the server see for this request. So that's really helpful. Something else to notice about this is I didn't set a special client request ID, so Operation Context created a random GUID for me. So now what this is going to let me do is I can now correlate this entire request of these 16 operations with the server logs. So again, we're all good Azure developers. We've enabled logging and metrics in the server. So what we're going to do here, I've actually got some logs that I've already downloaded. So you can see all the information here. These are they're delimited, so you can open them up in Excel and format them. So I've done that just for ease of use here. So you can see a couple things. A whole bunch of information was logged for me. I get the request URL. I get the request ID. So I could look up that one that had the exception. And then here's the client request ID. So I did many, many operations of this one client for this one operation with this client request ID. I can see that I was using the 2.1 library, so if you're using different applications, you can see which application's having issues. Then I can also see the size of the headers and the payload. And then one of the most important ones, if I can find it here, is application end-to-end latency and storage server latency. So end-to-end latency is first byte to last byte. The entire operation took this many milliseconds. The storage server latency is how long did the server spend processing this request. So what I can see here, so let's take this one. I can see that I'm on a slower network. It took 421 milliseconds to round trip this data, but the server only spent 7 milliseconds processing it. So if I see high latency, I may say, for whatever reason, I'm having slow networking on this request. And then I can look down for those exceptions. So I see here I don't have a content MB5 because I didn't receive all the data, but I can see the status code which is network error. So now, again, client-side logging, server-side logging, I can correlate these two logs together and get a client view. So here's my client log. I logged a whole bunch of stuff. I can actually find that request ID in here if I want for that exception. And now I can correlate that back to the server. I now have a complete view from both client and server about what exactly happened for all my requests. All right, so storage analytics. This provides metrics and logging. We've kind of already talked about logging. Metrics provide usage data per abstraction. Logging is per request, so you can include client trace IDs, different verbs, put, get, etc. And they're stored in your account. So you can enable this via the portal. It's very simple, a few buttons. And now you can monitor and diagnose your own applications. I highly recommend this if you're using SaaS or public access. If you're serving web content out of blobs, for example, and somebody posts it to CNN or some website, you start seeing a huge amount of traffic, you'll be able to see who is accessing storage on your behalf. So the logs are stored in Azure blobs. You can configure the logging levels separately. So, for example, I can have my blobs do all the operations and my tables only do puts. One thing to note about logging is that it's best effort, which means that it is possible that for some reason a role recycles before all the logs are pushed to the storage service. So if you're using this for billing, it's possible to lose a record or two. But if you're using it for general purpose auditing, debugging, this will work great. So here's how you enable it during the portal. I go in there, I click the things I care about and how many days I want to keep it. Why turn on metrics? We've kind of already talked about this. Figure out who's accessing what, client IPs, things like that. So here's just some example about metrics, what's logged. We'll skip through this. You can download the slides and look at all the information. Total ingress, total egress, latencies, percentage success. That's all useful. For blobs, you can actually get capacity metrics. So once a day, it'll actually write out how many objects do I have and how much size is it taking up. So I can now pay attention to that so I don't have any sort of surprises at the end of the month. And here's how you enable this on the portal. So you can see that these guys are stored in reserved containers. So there's $logs for blobs, and the metrics are in tables and $metrics. These two different resources have a different SLA for transaction count, so you don't have to consider any sort of logging traffic against your scalability targets in terms of transactions a second, anything like that. Again, the cost is only the cost of the size of the data. One note about this is that some client visualization tools won't visualize the $anything container because it thinks it's reserved. So if you're not seeing it in some sort of client tool, you may have to use the client API or use a different tool. All right, so summary. You're the expert on your scenario. You know what your growth targets are, how you're going to scale. You know the bandwidth per partition. You know how clients are going to access data. You need to deploy the best practices per service. So blobs, tables, queues, we've talked about that. Figure out, am I trying to optimize for latency throughput and come up with a strategy around that. Again, we highly recommend using the latest storage client libraries because there's just so many performance improvements there. Something else interesting to look at. Nasuni is a company that evaluates cloud storage providers. And so they recently released this report, State of the Cloud Storage Industry. This is from February. And so they did all of these performance benchmarks across all the different public cloud storage providers. So Amazon, Google, HP, Rackspace. And two things to highlight here. Azure delivered the best read, write, and delete speeds across a variety of file sizes and the fastest response times and fewest errors. The second one to look at there, Azure not only outperformed the competition, but we had 0 errors in the 100 million different reads and write operations that they did. So we've got multiple levels of redundancy baked in the system. The DFS layer actually has periodic data scrubbers that'll just check for bit rot, just to see if for whatever reason the hard drive corrupted some data, and it will actually replicate that out of a healthy replica to make sure you always have that quorum of healthy nodes. So there's a link to the blog post in the PDF there, a whole bunch of different benchmarks. You can kind of get an idea of what they saw there. So here's some future directions, things that are coming in the coming months here. Cores, so if you're serving web content out of blobs, specifically accessing them from a browser or JavaScript. Cores is what you need. The Windows Phone library will be available shortly. It's in testing. A lot of performance improvements. We're expanding platform support for different languages and different platforms. Geo-replication for queues. Read access to the secondary data center. So if you have geo-replication turned on, we're going to enable you to actually read that data from the secondary data center, which has its own scalability targets, and control failover at now the blob or resource level, which can be really, really useful. And then expanded reach. There's a blog post there about the new region build-outs. So resources here, a whole bunch of different links. One I'd like to highlight here is the Azure Storage Team blog. If you read that, that's where they post all of the new features, any issues that they've discovered in different platforms, and any sort of announcements or releases. The next thing, there's actually a build talk happening, I think, tomorrow, and they'll be announcing a lot of the new features in more detail. So if you look at that, you can see all the different things that are coming online. There's a very interesting write-up that we did about a .NET client update. So they basically updated as part of the regular QFE process, and they changed the semantic of the HTTP web request. And unfortunately, for some clients, it's made it so that they started using up all the ports on the system. We pushed a patch to NuGet right away, so that clients that were on the latest NuGets didn't really see this. There's a fix coming out from the .NET platform itself. It's a very interesting read. I recommend that as well. And then lastly, there's this SOSP paper, so this ACM operating system symposium. So if you care all about the CAP theorem and you want to see how we do what we do, how the DFS system works, all the internals, this is the talk and paper you want to pay attention to. All right, so we got just a couple questions, a couple minutes for questions here, and then I'll be available in the front and at the booth. So, anybody? All right. It's a lot of information. The slides will be up on Channel 9, and then we'll also try to post the sample code for all the different services and benchmarks. A few more resources here. Channel 9, TechNet, MSDN. If you have an MSDN subscription, I highly recommend you go in there. You can activate a free Azure storage account. There's a bunch of different Azure resources you already have. So you can play around this for free. If you install the SDK, there's a development emulator for storage and compute. So you can actually test out your scenario before you even deploy anything to the cloud. And then here's the QR code. I'd request that you do the evaluation so I can know how we did. And again, I'll be down in front for any questions. Thank you.